Welcome back. In previous videos, we kept things pretty abstract and general when discussing properties of discrete choice models and conditions that they impose on what we can and can't infer. Today, we're going to make these abstract concepts more concrete by deriving one of the most important mathematical formulas in all of discrete choice modeling, which is the Logit probability function. This mathematical derivation will show us exactly how individual preferences translate into observed choices in the data. Don't worry if the math seems a little intense. I'll walk you through everything that you need step by step. Let's start with a very simple situation, which is we only have two choices, and we're going to assume that the epsilons are drawn from a type 1 extreme value distribution. Where does this come from? Well, it's a long story and not something we need to cover right now, but just know that like the normal distribution or the uniform distribution, there's a distribution called type 1 extreme value, and it has a very special functional form for both its cumulative distribution function and its density function. The cumulative distribution function, if we assume that it's a standard type 1 extreme value, takes the form of e to the negative epsilon, and then the PDF is e to the negative epsilon times e to the negative epsilon. So this is called the extreme value distribution of type 1. Sometimes it's called the Gumbel distribution as well. And we're going to assume that the epsilons are drawn from this distribution. And we want to know the probability of choosing option 1. We can apply our probability and utility maximization formulas from prior videos, where we're comparing the utility from both the observable and the unobservable components of option 1 with that of option 2, and this probability will hold under these conditions. So then we can rearrange terms so that we put both of the epsilons on the same side of the inequality, and then we can further isolate just epsilon I2 as the only thing on the left-hand side of the inequality. And this will be helpful when we think about applying the CDF to this probability. So since there are two things that we don't know, we need to have a double integral to solve this probability. So let's start with this double integral. We're going to put the indicator function that the event that the probability corresponds to is true. So that's the first component. And then we have the density function of the joint distribution over these two epsilons. And then we need to integrate both of them out because we don't know either of them. So this is hopefully somewhat familiar from a prior statistics class that you've taken. Now, the key assumption here is that the epsilons are independent and identically distributed, which means they are IID. And if they are IID, then we can express their joint distribution as the product of the marginal distributions. And this will be a very important thing to simplify this math. And then once we've applied this joint distribution becomes the product of the marginal distributions condition, then we can separate this joint integral. So this double integral over the joint distribution can now be a nested integral or a hierarchical integral. So we can basically evaluate the inside first and then the outside, and that will make things a lot simpler to do this double integral. So all I've done is just apply this condition, and then we separate out the stuff that has to do with epsilon 2 from the stuff that has to do with epsilon 1. And what's inside this set of braces? Well, this is just the CDF of epsilon I2 evaluated at this expression. So this is just the definition of the CDF. The CDF will give us a probability of some event, and what you see in the integrand here is exactly the definition of that probability. So we can see that that's the CDF of epsilon I2, and then we can simplify this expression. We can say capital F is the CDF of epsilon I2, and then we can put where we're evaluating the CDF is this expression here, epsilon I1 plus UI1 minus UI2. And then we carry down the f of epsilon I1 from here and the d epsilon I1 from here. And then we're going to put bounds on the integral now. So it was an indefinite integral, now it's a definite integral, and we're going over the entire real number line because that's the set of values that the extreme value distribution can take on. So we've taken this double integral and we've turned it into a single integral, and we have a CDF here. Now let's apply the functional forms for that CDF from the first slide. So we know that the CDF has this particular functional form and the PDF has this particular functional form. So if we apply that, then we can get this expression, which doesn't look particularly intuitive, but we can do some algebraic manipulation. So you'll notice that we have some like terms here with this e to the negative epsilon in two different places, and we can express that in this way. So we've taken these big e's here and we've turned them into an exp just to kind of make the notation a little bit easier. And then we have this e to the negative epsilon 1 that's being hit with a 1, or this e to the negative u2 minus u1. So there's just some algebra here that is manipulating properties of exponentials and combining like terms. Then we can do what's called substitution, or U-substitution, as I learned it in calculus, which is we can notice that there's a similar set of terms here. And if we use this as t, then if we take the derivative of this, we get this times dt. And then we change the bounds of the integral to respect the new basis of this t and dt. So instead of going from negative infinity to infinity, it's going from infinity to 0. So this is how we express that same integral in the new basis with dt instead of d epsilon. And now we have something that's very tractable, because we have a constant times an exp of negative t, and then we have a negative dt. There's a bunch of ways that we can simplify this further. We could evaluate the negative here, flip the bounds of integration, or we can just evaluate it directly. We'll just flip the bounds of integration and get rid of that negative sign, and then we can take the antiderivative and then evaluate it at the bounds of integration. So the antiderivative, this basically amounts to e to the negative 2x, for example. So what would the antiderivative be? Well, it would be 1 over negative 2 times e to the negative 2x. So that's what we're doing here. And then we can evaluate this at 0 and infinity. E to the negative infinity is going to be 0, and e to the 0 is going to be 1. So we do that, and we get this expression, and then we can simplify it into this formula, which is a familiar formula and pretty simple formula. And that is how we get the actual probability for the utility of option 1 being higher than the utility of option 2. And the nice thing is that this generalizes to any number of alternatives. And instead of having e to the u1 plus e to the u2, we just have the summation of e to the u of however many options we have. So if you're interested in the multinomial or the generalization to all capital J alternatives, then you can consult section 3.10 of Train's textbook from the 2009 edition. So what we've just derived is pretty remarkable. We have this really convoluted double integral, and it simplifies down to a very, very simple and elegant algebraic formula. All we did was we assumed that the epsilons were distributed type 1 extreme value, and then we took those assumptions and simplified until we got a very tractable functional form. So this Logit formula forms the backbone of discrete choice analysis, and we'll spend several videos moving forward talking about the advantages and the disadvantages of using this formula. We'll also talk about how to estimate the parameters of the utility function given this assumption about the epsilons being type 1 extreme value.